Hi, we're going to talk about ideal gases, which is section 4.3 in your chemistry book. When we're working with ideal gases, we use PV equals nRT, which is called the ideal gas law equation or ideal gas equation, PV equals nRT. To start out, we want to know what those different values stand for. The P is equal to pressure, which can be given in atmospheres or kilopascals for our work. Volume will have to be given in liters. N is the number of moles, the R value I'll talk about in a second. And T is temperature, but it has to be in Kelvin. If it's given in a different value, it has to be converted to Kelvin in order for this to work mathematically. Let's go back to R. R is the ideal gas constant, or the universal gas constant, and we have multiple possible values for R. The one that's given in your book is this top one here, which is R equals 8.31 liters times Kelvin, liters times kilopascals per mole Kelvin. There's another value that you'll use just about as often. That value is on the bottom here, and this is found on the back of your Plainsman periodic table. Both of these are. And that is R equals 0.0821 liters times atmosphere per mole Kelvin. And you can see that the difference in these, besides numerically, is in the pressure units. The top one uses kilopascals and the bottom one uses atmospheres. And it is the pressure value of a problem that's going to determine which of these two R's you use. I'm going to go through an example now for the ideal gas law, so PV equals nRT. And I'll be looking at question number 26 in the book. For question number 26, we are given a volume of 6.85 liters. We're given a temperature in Kelvin already, so we don't have to convert. That's 621 Kelvin. Given a pressure value of 1.89 times 10 to the third kilopascals. So from that, we need to determine which R value we're going to use in PV equals nRT. So if you look at the back of your Plainsman periodic table or into your notes for the two different R values, they would be found here under the equation PV equals nRT. And we can see that given pressure in kilopascals, we need to use the kilopascal R value, which is 8.31 liters times kilopascal per mole Kelvin. So I'm going to write that in to my problem set here. And then we'll be solving for N for moles, liters times kilopascals per mole Kelvin. So these are all of the values that I need to solve this problem. The next thing we're going to do is rearrange our PV equals nRT in order to solve for N. So you can see that in this top equation, we need to divide both sides by RT and get N equals to PV divided by RT. Okay, I did that in the top equation. And I'll put at the bottom that N equals PV divided by RT. So I rearranged my equation there. And now I'm going to plug in the values. So my P value, my pressure, is 1.89 times 10 to the third kilopascals. I'll multiply that times my volume of 685 liters. And you need to make sure that you put units in here. And the bottom, I'll put 8.31 liters times kilopascals per mole Kelvin times the temperature, which is 621 Kelvin. Okay. So this is the work that I've set up. That is N equals all of that. Now we're going to take a look at units to make sure we set this up correctly. I can see that kilopascals on the top for the pressure can cancel out with the kilopascals of the R constant value. Liters can cancel, top and bottom, and Kelvin can cancel on the bottom to the bottom of the R value. That leaves us, after I cross those out,
1 over moles, which is the same thing as moles. So I'll circle that value. And since we're trying to solve for moles, and that is the type of unit that is left when we do all the work, that means we've done this correctly. And when we do the math for this, that leaves us with an N value that is 251 moles. So check your math there and see if that's what you got. Okay, so that's how to work problem number 26. And you need to check and work the other problems as well. Now let's look at the idea of ideal versus real gases. So to introduce you to this, I'd like to talk a little bit about kinetic theory. In kinetic theory, there are some what we call postulates or assumptions that we make. So I've written those down here. One is that gas particles are in constant motion. The temperature is the average kinetic energy of the particles. And as we increase our temperature, here it says increasing Kelvin temperature, we increase the average kinetic energy. We also have that pressure is from collisions of particles, that's with each other and with the walls of a container. And gas particles are assumed to have no volume. So on this one, you can see that I've underlined that assumed part in red because this works when gases are acting ideally, but not when we get to the concept of real gases. The next one too, gas particles are assumed to have no attractive or repellent forces, meaning that the collisions are perfectly elastic. So those last two are going to come into play when we compare ideal with real gases. When we have ideal gases, that means that all of the gas laws, including the simple gas laws and the ideal gas law, will mathematically work when we put in the values for the gases. But the next piece over is, do gas particles truly have no volume? And the answer to that is no. Particles, even though the volume is very small, there is a volume. Under ideal conditions, the volume of the particles is so small compared to the empty space between the particles that we can say it's not significant, and the gases will act ideally. There are conditions, though, of temperature and pressure where the volume of the particles starts to come into play. What type of attractive forces exist between all molecules and how strong are these forces? Remember that anything with electrons can have dispersion forces or London dispersion forces, and those tend to be fairly weak attractive forces when we have small molecules. Now, the key beneath that says that real gases differ most from ideal gases at low temperatures and high pressures. And that is what I'm going to explain now, that low temperatures and high pressures, I'm not going to give you a numerical value for low temperature or high pressure. That's going to depend on the gas, depend on the sample. But under those conditions of low temperature and high pressure, that's where these assumptions of no volume and no attractive force start to break down. So let's start with low temperature. At low temperature, the particles we know will start to move more slowly in terms of their average kinetic energy. And that means a collision is not going to be as strong and as elastic. It's possible for interactions to start to come into play. So that's where this assumption of kinetic theory, no attractive or repellent forces, starts to break down. And in fact, the gas will start to move toward a situation where eventually it would condense and not be a gas anymore. But we're still talking about gases. So we're not talking about condensed gases. We're talking about increased attractive forces and non-elastic collisions. The other condition that is going to be considered a real gas condition besides low temperature is high pressure. So let's consider a sample of gas where we have a particular volume. Now, if we decrease that volume, which increases pressure, we're decreasing the empty space between particles, and the volume of the particle itself is going to start to become significant. And we can no longer assume then that there is no volume for the particles, and that's when gases tend not to have ideal behavior. So low temperature, means that gases will start to behave in a real way as opposed to mathematically work in an ideal way. The other situation is high pressure, where the volume is decreased, the pressure is increased to the point where the gases start to have interactions and attractive forces that come into play, as well as the volume starts to become significant. So under those circumstances, gases will no longer behave ideally. Mathematically, they won't work for PV equals nRT or the other simple gas laws, and they will start to behave as real gases, not ideal gases. So if you need some more information about how to work with PV equals nRT or with the ideal versus real gas concepts, you are welcome to contact your teacher or to look at the videos that we have listed below at the end of this segment. Thank you.